Hey, welcome back. Today we're looking at 5.3 part 2. Today we're focusing on graphs. So we're going to be using some Desmos and we're going to be trying to figure out how to sketch these graphs or have an idea what they look like without necessarily having to use a graphing utility or graph it point by hand. So let's go ahead and graph y equals 2 to the x in Desmos so we can take a look at what an exponential function might look like. So we're going to say y is equal to 2 to the x. All right, so let's close this up. Now notice that what we have here is a graph that's on the left-hand side, it's very close to 0, and as it grows very slowly until we hit a certain point, and then we increase very rapidly. All right, so that's the characteristics of an exponential function. So as we are to the left side, usually unless we have a transformation, we're growing very slowly, and at a certain point we increase well, exponentially, but what that means is that it increases a lot really quickly. So one thing that is modeled by kind of an exponential function, because we can't grow forever, is the population. So if we're looking at bacteria, you start with 1 bacteria, maybe an hour later you have 2 bacteria because it doubled, and then you have 4 bacteria, and then so on and so forth. But once you start hitting bigger numbers, when they start increasing, it gets really huge really fast. All right, so let's look at some of the questions here. So it's asking us, do we have a horizontal asymptote? So if we look at our graph here, our horizontal asymptote is the x-axis. If we're trying to write it in terms of y, we'd say y equals 0. And we know that if we look back on our graph, because what happens is it gets ever and ever closer to 0 if we go to the left here, all the way towards infinity, but it never quite touches. So again, a reminder that horizontal asymptotes describe the end behavior. So if we're following this towards the end on the left-hand side, that's getting closer and closer to 0. So our asymptote is at 0. All right, if we're looking at initial value here, we're looking at the y-axis or the y-intercept, and we have initial value of 1. Now the domain for any exponential function, notice if we trace this, we could trace this forever to the left and forever to the right. So our domain for any exponential function is going to be all real numbers. And then for our range, because we have a horizontal asymptote that this graph doesn't cross at 0, right? Our range is going to be everything above 0 because our function is increasing from there. So let's make sure we write this both ways depending. So we're going to say x such that x is greater than 0. And this is in set notation. Notice we didn't say greater than or equal to 0, because if we follow this to the left, it gets ever and ever closer to 0, but it never quite reaches 0. So yeah, make sure you don't put an or equal to sign there. And likewise, when we're writing this, oh, sorry, I should say y. That's a mistake, right? Because our range deals with our y values. Y such that y is greater than 0. And then for our interval notation, we'd say the lowest point at 0. There's a parentheses there, right? Because it doesn't hit that point. And then it goes all the way to positive infinity. All right, so pretty simple. The graphs of exponential functions pretty much look the same. When you're working with the quadratic stuff and families of functions and the flips and shifts and rotations, we're going to be covering that next. Right, so notice this one looks a little different y equals 2 to the negative x minus 3. It's a little bit different. First of all, we have this negative x, and then we have this minus 3, right? So if we think about this being the reworked function, right, with all the different types of transformations that can occur and variations in the equation of it, and we apply what we know about quadratics to this same idea, then we should be able to sketch this pretty well. So for our families of functions, we know that if the a is negative, whatever is in front of our function, then it flips over the x-axis, right? So one way to think about that is if we have our function, and this goes back to quadratics, right? Y equals x squared. If it's a positive, it opens upwards. If it were negative x squared, it opens downwards. So same idea with our exponent. Our exponential, if we have a negative in front, then all that does is flip it over the x-axis. Okay, something that we didn't encounter in quadratics is if we have a negative x, and that's because if we flip our quadratic over the y-axis, it's the same thing, right? If we flip this, because it's symmetrical, over the y-axis, it's the same exact parabola. So in this case, because we have a non-symmetric function for our exponential, right? It looks like this. If we have a negative in front, it would flip it over the y-axis. So let's say this is our y-axis here. It would flip it over the y-axis so that it would look like that instead. Okay. And then the rest of the stuff inside of our parentheses. So with our x, if we have a negative or minus h, then it actually goes right. So yeah, that's the weird one, right? You think that plus would go right and minus would go left, but it's actually flip-flop. And then the last thing, that k outside tells us if we're shifting up or down. So positive up, negative down. All right, so let's see if we can sketch this. Let's draw an exponential function. Right, so we drew the base one already, or we kind of looked at it in Desmos, right? We found all the characteristics. We said the horizontal asymptote is 0, that we have an initial value of 1, and it just kind of increases after that value, okay? So let's go ahead and sketch the base one. So the base one looks kind of like this. Right, so this is just going to be, if this were, whoops. Something's not right here. This were just y. I'm not sure why I'm not able to write. Oh, that sucks. So let's say y. My finger works terribly for this. Oh, this sucks. Let's try a different thing. I think I got something in here. This one's not working either. Y, okay, there we go. Y equals 2 to the x. Sorry, this pen's a little bit harder to write with. Okay, so what we're going to do is, in this case, we're going to note that this is a negative x. So negative x means that we're going to flip on the y-axis. Okay, and then we're going to shift. The minus 3 says we're going to shift down. So let's do one at a time. So the first thing, we're going to flip it over the y-axis. So it looks like that. Sorry, this pen sucks. And then we're going to shift down 3. So 1, 2, 3. Let's do that in blue. Okay, so you're going to try to draw the same thing, or a similar thing. Okay, so this is going to be the graph of y equals negative, 2 to the negative x minus 3. Maybe my pen needs a charge, so let's try to plug it in. No, that won't work because my other iPads did. Let's plug it into my phone. See if that'll charge it up a little. Okay. All right, so yeah, using the idea of families of functions, the family of functions idea works for any function that you have. So if you can apply it to quadratics, awesome. If you can apply it to linear, awesome. If you can apply it to exponential and any function that you find, like if you find an absolute value function, it works the same there too. So the more familiar you get with it, the more comfortable you'll be working with functions. All right, so let's look at the next one. The next one says y equals negative e x to the negative 3, and we're trying to find domain, range, horizontal asymptote. Okay. So without graphing it using Desmos, let's kind of get a picture of what's going on here. So we're going to use that idea of family of functions. So the first thing is we have a negative in front. So if we go back and see what happens if we have a negative in front, okay, so that means we're going to flip over the x-axis. So one thing that's happening here is we're going to flip over the x-axis. Whoops. Sorry again about my handwriting. Okay. What we also have here is inside, well, technically there's no parentheses, but there's implied parentheses up here, right? Because it's all in the exponent. So if we refer back here, inside, if it's a minus, then we shift right. Okay, so shift 3 to the right. Okay, let's see if I got some charge on my other pen. All right, so if we think about this, all right, if we flip it over the x-axis, all right, we're going to have something like this. And then we shift it 3 to the right, then it's just going to go to the right 3 units. So the domain we said earlier doesn't change, right? So the domain is all reals. The range, because we didn't move it up or down, then we still see that our horizontal asymptote is 0. So for our range, we have 0 to infinity again. In set notation, that would be y such that y is greater than 0. And then our horizontal asymptote, working off that idea of range, our horizontal asymptote is going to be y equals 0. All right, and we can even go ahead and check. So negative e to the x minus 3. So let's check it on Desmos just to make sure, and we'll leave that base function there. So we have negative, where's my e? E to the x minus 3. I don't like that. Let's put parentheses there just to make sure it stays together. X minus 3. And then when we graph it, oh crap. Well, I did that wrong, right? I was getting careless. All right, so back here, we said that it flips over the x-axis, right? If the a is negative, it flips over the x-axis. So what this is going to look like is actually this. Right, so it shifts right, but it also flips x-axis. So this one we got to change for our range. Right, because now it's below the x-axis. So our range is going to be from the top now is going to be 0, and the bottom is going to be negative infinity. So when we write this, we have to say y such that y is less than 0. And our horizontal asymptote didn't change, right? We just flipped it over the y-axis. If we continue this way to the right, it's still going to, well, shoots. Well, I screwed this one up. Not too bad though. Let's change colors. So this would be y-axis. So it flips the y-axis. Sorry about that. And then it shifts 3 right. So let's do that in a different color. Okay, so this is the actual one we're looking at. So the information is the same. I just drew it funky because I didn't go all the way back and restart. Okay, and then if we look at our graph is in blue, and it should reflect that, right? Okay, awesome. Oh, and I guess that's it. Oh yeah. All right, so just when you're doing your work, you can use the graph if you want to. It's just to get you familiar with the family of functions idea, or refamiliarize yourself with that concept. If you have an idea of what the base function is for any function, then you should be able to apply those ideas to have an idea of what the graph might look like, right? Just by looking at the function. So it's very helpful because we might not always have graphing technology at hand, even though you could probably if you have an app on your phone. But it does help when you're doing like a college exam or some stuff like that. If you have an idea of what this function might look like, so that you don't have to take the time to graph it out and do all that stuff. And you can probably gather enough information just from the function itself to come to a conclusion. It's very helpful, especially on time tests, such as like the SATs and stuff like that. So yeah, if you have any questions, please write them down. We can talk about them next class. Good job today.